All right, we're chugging right along to the fifth question of this year's AP Calculus BC exam. So this is the fifth FRQ on the non-calculator portion. And we're given some function f. No, actually, I should say we're actually given some information about this function f. We're told that it's twice differentiable, and we know that f evaluated at 0 is equal to 0. And we are given information about values of the derivative f prime in this table here. So to start off, it says that for some value greater than or equal to 0, we've got this function h, which is defined as being this definite integral here. All right, so it's defined as h of x is being defined as the integral of this function from 0 to x. And it wants us to find the value of h prime of pi. So looking at that carefully, it's really just the fundamental theorem of calculus at work here. We know that h prime of x, the derivative of h of x, is really just going to be this integrand, right? So we can say that h prime of x is equal to the square root of 1 plus f prime of t squared, okay? So then if we're then trying to find h prime of pi, that's just that function evaluated at pi. So f prime of pi squared. So I'll put all of this in parentheses. Let me write that a little bit more neatly. Okay, and this is where the table comes in. We're going to look at our table. What is f prime of pi? Well, we're told that it is 6 right over there. So we're just going to plug that in. 1 plus 6 squared. And I can actually clean that up a little bit. 1 plus 6 squared. I should probably clean that up as well. Doesn't hurt to be neat. All right, 1 plus 6 squared, and that's going to be root 37. So that's part A. Okay, and I'll move this. Oops. I'll move. It's all right. I'll just leave it there. Okay. All right. So now moving on to part B. Well, what information does the integral from 1 square root of 1 plus f prime of x squared, what does that represent about the graph of f? And this is sort of either you know it or you don't, but looking at this, 1 plus f prime of x, what do we recognize about that? Well, it just gives us the length of the curve, f between our bounds, x is equal to 0 and x is equal to pi. All right, so it's just the formula to find the length of any curve, okay? All right, so I need some space for part C because we've got an Euler's method problem. So let's work down here. So using Euler's method, starting at x is equal to 0 with two steps of equal size, approximate f of 2 pi. So a lot of times students will just write this out using equations, and that's totally fine. I personally like to use tables. It just helps me organize my work. Not necessary by any means, but if I just set up my table here, I can kind of just start filling in the information that I know, right? So dy dx. And notice we're not actually given the differential equation, so we're not given dy dx, but we're actually going to use our table there, okay? And then we're also going to need one column for delta y, and you can also call that y prime, right? Which is just going to be dy dx times our step size, all right? So we're starting out at x is equal to 0. So that's our first value. And it isn't written here, but it was written back again if you look back into the previous problem, we're told that f of 0 is equal to 0. So if I were taking the test, I would highlight something like that and just make sure I'm aware. So f of 0 is equal to 0. So I already know the first two values here. So Euler's method is using dy dx to give us information about an initial condition, I should say. It's using the initial condition and our derivative information to approximate what our actual function is doing. That's the whole point of Euler's method. It's another way to try to approximate what our function f is doing based on what we know using the derivative. It's leveraging derivative information. So dy dx, when x is equal to 0, we're told that f prime of x, this is our dy dx, if you will, is equal to 5. So we have that value of 5. So what is going to then be the change in y? The change in y is dy dx times delta x, right? Right, that's how we get that delta y. So what is dy dx times, actually, probably need to just erase that part. I can leave it here, it doesn't matter. All right, so we've got 5 times, and what is our step size? What is our delta x? Okay, so I'm going to say dx or delta x. What is our step size? Well, if we want to go from 0 and we're trying to approximate 2 pi, then if I'm taking 2 different steps, let me actually do it like this. If I'm taking 2 different steps, what does this step size have to be? Well, it's got to be pi, right? So I would just say 5 times pi. So that's our vertical change. That's our change in y. So our previous y value had been 0. And so from 0, we're going to add 5 pi to it. So now we're at 5 pi. Okay? And we're going to repeat this again. So what is dy dx when x is now equal to pi? Well, that is going to be 6. And again, our dy dx times our delta x, or our change in x, and again, that was pi. We wrote this was pi. 6 pi. So we're going to add that now to our previous step. So from 5 pi plus 6 pi, we're now at 11 pi. Okay? So using Euler's method, we can say f of 2 pi is equal to, or I should say, where it's approximately equal to 11 pi, based on what we found using Euler's method. Okay. All right, and then finally part D. It's now asking us to find the integral of t plus 5 cosine of t over 4 evaluated at dt. So if you were taking the test, you probably took a look at this and thought to yourself, okay, what integration techniques or strategies can I use here? And if you look at it carefully, you hopefully notice that it is a problem that can be solved using integration by parts. So this we're going to identify as our u, and this is going to be our dv, right? So u is going to be what we are differentiating. So right underneath, I can say that du is equal to 1 dt. So the derivative of t plus 5 is 1 dt. And the integral of cosine of t over 4 is going to be 4 sine t over 4. Just using kind of reverse chain rule here. Okay? So then we can say that what we're trying to find, the integral of t plus 5 cosine of t over 4 dt, is equal to, and those of you who've taken my class to know the formula that we use, we would say ultraviolet minus the integral of v du. So ultraviolet voodoo. So we're going to write, so ultraviolet minus the integral of v du. So let's fill in what we know. What is u? T plus 5. What is v? 4 sine t over 4. Minus the integral of v, which again is 4 sine t over 4, du, which is going to just be dt. So we can leave this part alone. That's fully integrated. There's nothing else I need to do to this. And then minus the integral of 4 sine t over 4. Well, that's just going to be 4 times 4 cosine of t over 4. And since this is an indefinite integral, we've got to make sure to include our constant of integration. And I'm just going to clean that up. You don't have to simplify for the AP exam, but I always like to just write that. I don't want that to be interpreted as 4 times 4. So there you go. There's the integral to t plus 5 cosine of t over 4, which we got by using an integration by parts.